So I've got a little bit of a dramatic title here, but I'm hoping by the end of this talk you'll believe me. So we'll see how that goes. I'm Christine Beavers. I'm from the Advanced Light Source, which is a little synchrotron on top of the Berkeley Hills, and I do a lot of single crystal diffraction. And so we're going to talk about what is crystallography. Well, thankfully a lot of you actually know, so I don't have to try and convince you it's not metaphysical. It's physics. It's looking at the structure and properties of crystals. I believe it was actually in Knoxville one time at a crystallographic conference. I was asked, oh, is that metaphysical? No, it's physics. No healing crystals here. They only cause us ulcers. So what is a crystal? It's a periodic arrangement of matter. So every crystallography class everywhere in the world, period, the end, shows Escher diagrams. Escher diagrams are the best for making you think about, oh, things that tessellate but aren't always that regular. So we can all think about shoes and shoeboxes and squares, but lizards, a little bit harder to imagine until Escher came along. But to make things really easy, the idea of a crystal is a three-dimensional repeating array of atoms or molecules. And I'm going to use shoeboxes. Shoeboxes because you can stack them, and they have things in them. So one-dimensional array of shoeboxes would just be a line. Two-dimensional, now you have a wall. Three-dimensional is what we think of with our crystals. So we take those shoeboxes and we fill them with molecules. And this is an awesome slide made by my friend Mark Warren, who's at Diamond Light Source. Back when he was a grad student many, many years ago and came to the beamline, he was bored, which happens on the beamline sometimes. So he made a slide that demonstrated periodicity of molecules in boxes and then translated them into what the actual crystal would look like on a molecular scale. It used to do one more move. I think I might have killed it. It used to move all the molecules back up. But anyway, you get the idea. So here, simple organic, it is packed in this shoebox, and then you're repeating forever, and this is what the actual crystalline lattice looks like in atomic terms. So that's all well and good. That's the idea. How does the actual experiment proceed? What are we doing to go from, well, we have an idea of a shoebox to, oh, we have some molecules in it. How do we get those molecules? How do we know about the atom positions? Well, we start out with a crystal and an X-ray beam. So that crystal right there is probably about the best crystal you're going to find anywhere. It's a really good-looking crystal, and then we proceeded to abuse it, which I'll talk about those techniques later. But it gave nice diffraction. Not perfect, but pretty nice. What we're looking at here are the spots. You've been hearing about Bragg's law, reciprocal space, and diffraction. So that is what an actual data image looks like when you apply Bragg's law in 3D. You get intense reflections at the points that satisfy Bragg's law. So I was told to not beat Bragg's law to death. I assume that happened yesterday. My condolences. So now I'm going to talk to you about what the actual experiment, how it proceeds. So we have crystal selection. You've seen that. Usually it's not so simple. You have a batch of horrible things, and you try and pick something beautiful out of it. And we go from there. This will be my flow chart. I'll be telling you about all these things in theory, and then we'll go on to more advanced versions of the experiment. Okay, that was weird. Ended up with a double. All right, now we're going into data collection. Oh, this slide got put in the wrong place. Okay, so you've all seen a diffractometer if you've done your crystallography, right? Yeah? Okay. So the gist of a crystallographic experiment is you are rotating your sample while taking exposures of the X-ray beam hitting the crystal. And we have a number of different circles that we should define. A diffractometer can be considered a 3-circle or a 4-circle. The 2 circles you generally always have. It's a 2 theta circle, which is the detector to X-ray source angle. Then we have an omega circle. Omega is where this block right here that your sample is mounted on is rotating with respect to the beam. And on top of this block, you always have a phi circle, which is a spindle axis. If you do a protein crystallography experiment, I don't think this is that kind of school, but if you did, if you veered to the dark side, you would mostly only see phi circle diffractometers. This is what you should have seen, or something similar. I'm not going to say any brands are better than others, but this is a very typical single crystal diffractometer, except this one is at a synchrotron, so it is on its side due to the polarization of the beam. You would usually have it sitting on the base, which is behind here in a lab source, because the polarization is different. So here's our 2 theta angle. Here's the detector. That is omega right there. And that block right here is the phi block, and the phi rotation occurs at the end of that block. Other important things in a single crystal experiment. Well, duh, X-ray beam, right? Comes in this case, from the right, goes through, there's beam stop to keep it from hitting the detector. We have a timing shutter, which is actually becoming a thing of the past. This may or may not be pertinent to you, but most systems in the next couple of years will be progressing to shutterless data collection and no more timing shutters, because we'll have CMOS detectors instead of CCD, which don't require dark time to process the images. So this is actually out of date as far as the beamline that I took this picture. They don't have that anymore. Most crystallographic experiments occur at low temperatures. So we're working at liquid nitrogen temperatures, sometimes even liquid helium. In some cases, if you wanted to go really low, you could have a closed cycle cryostat, which would actually be really a box around your sample, and it would be pumped down very, very low. And right in here, if you see that, that is the mount that the crystal is mounted on. That is an X-ray transparent Mitogen type Kapton loop. So it used to be that everyone mounted their crystals on glass fibers. That's not so much the case anymore. Okay, so that's the general schematic, and of course that's our detector. And this seems to be very slow today. Okay, as I said previously, we have an X-ray beam coming in, and it is impacting the crystal that is rotating, not usually so much on the phi axis, but you will move it to different settings on the phi axis before rotating it about the omega axis. And while we're doing this rotation, we are snapping off images of how the diffraction changes. So we are basically taking almost tomographic type images of snapshots of the diffraction during the rotation. So that's great. We've taken thousands of images, and then what do we do with them? Well, first, we want to determine our unit cell. So these are the dimensions of the shoebox, essentially. And that is directly related to the positions of the spots, well, inversely related to the positions of the spots on the diffraction images. You have to bear with me. My computer still thinks it's California time, too, and very, very early. All right, so this is a diffraction image. We have spots. We run through our 3,000 images. We determine the positions of the spots with respect to the diffractometer coordinates, and we get a lattice of spots. It looks a little messy at this point because we have numerous different phi positions that may or may not be perfectly related to each other. And then we use math, directional cosines, to determine the spacings in between the spots. And basically, the smallest common spacings are usually related to the axes here. This one is cubic, not the greatest example, but it's what I had at the time. Also the simplest, and you can see we get an axis, and then we get an ESD, or an uncertainty, on that axis. The smaller this is, the better, the more confidence we have in our unit cell being correct. Usually you don't see something quite that nice until you've actually recycled your a couple times. Okay. So okay, we've got a unit cell. But unit cells only battle. So now we only have the size of the shoebox. Most of us don't care about the unit cells so much because a lot of things can go in a shoebox. We don't know how things are hooked up. We actually want to know what's in the shoebox. So we need to know intensities of our spots really well. And so for that point, we go to integration. So once again, we go through our thousands of images, and we profile our spots, and we figure out what intensity is contained in that diffraction occurrence. And so this is rather exhaustive. With some of the programs, it used to take hours. It's a lot faster now that everything's multi-core, and I'm sounding like one of those people who's saying, oh yeah, in my day I walked uphill both ways to school, but it used to be slower, and now it's not. It's getting better, especially with the fast pixel detectors. There's a lot less work into estimating the intensities, because here, this is a detector that works by the X-rays, come off the crystal, hit the detector, hit a phosphor. So this phosphor converts X-ray photons into light photons, and then that goes on to a visible light sensitive sensor. So there's a lot of conversions there you have to work in. Now the new fast detectors, like the Pilatus and things like that, they're direct detection. They just detect X-ray photon. Oh, you have an X-ray photon. Oh, I'll count it. That's all. So it's getting a lot easier now, actually, to do intensity integrations instead of having to say, well, this phosphor makes this many visible light photons for this many X-ray photons, and doing all that. You don't have to do that anymore as often, which is nice. Okay, so we have intensities, we have positions, we have unit cell parameters. We can actually go on now and get closer to what we really want. There are a couple important things in the way, though. Absorption correction. It's funny how many times people tell me that I don't care about absorption correction. Oh, well, you're at a synchrotron. You have a lot of flux. You don't ever have absorption correction, right? Well, no, that's not true. I work at a soft X-ray that does hard X-rays, so I'm not at APS. But even if you are at APS, if your crystal's big enough or your beam's small enough, you're not going to have perfect isotropic diffraction. So if you have a perfect spherical crystal, you can rotate that in the beam, and the beam is always seeing the same volume of diffraction. That's pretty much the only time you don't need an absorption correction. Everywhere else, non-spherical crystal, non-perfect beam, you need an absorption correction. So what we see right here is a normalized scale factor for images, i.e. reflections were a lot weaker here, then they got stronger, then they got weaker, then they got stronger. So this is anisotropic diffraction of a crystal. You've rotated this crystal, the beam is cutting through a different volume, you have to adjust for this. So we try to apply smoothing factors to approximate the geometry of the crystal. You can do this a number of ways. You can do actual face indexing. If you are able to do this, if your crystal's big enough, you can identify faces, then you can apply a numerical absorption correction. In a lot of cases, we can't do that. Our beam is, our crystal is anisotropic, but small. And so we need to actually do a empirical correction, so multi-scan. So you compare your different scans, and you scale each scan independently, depending on what the anisotropic behavior of the crystal looks like. So, and I have more notes on that in my presentation if you want to get a little bit deeper into it. Okay, so we've done absorption correction. Now onto space group determination, which is something I can't spend too long on, but definitely it's a topic that everyone should spend some time looking on. It's really impressive, actually, what you have to go through when you have an ambiguous space group. And recently that was a part of a major publication I did with some collaborators. But in short form, this is a slice of reciprocal space. You see some of these spots. So the big black and blue ones, they're the more intense ones. Then we have the little tiny multicolored ones. Those little ones are present. They're reflections that are present but are weak. And why are they weak? What is going on? So you could say statistically that a lot of these weak ones are absent. Depending on what the uncertainty is on their intensity, you could say that they are systematically absent. And this is due to interference effects from translation symmetry. So in this case, this is the H, no, oh, yeah, that's wrong. Oh, Lordy. Oh, it's a good day. Yeah, so you can see that there is a weakness when that should be H, but there's a K there. So if we're H, this is the H0L plane, and we have absences here when H is odd. And so we don't have anything in the L direction, because it seems like all the L direction, they're all present. So this weakness in the H direction is due to a glide plane, because you have this translation every half, and you actually produce this weakness. So it's almost like a halving of the unit cell, but that's only an interference effect. So these are the kinds of things you look at in your intensities to determine what your space group is. So in this case, we'd say, oh, we have a glide. If you were really invested in looking at all the possibilities that you might have for, say, an orthorhombic space group, you would want to go into the International Tables of Crystallography, Volume A. And this is one of the massive, this is only a part of one of the massive orthorhombic space group tables. And you'll see there are different kinds of exceptions listed. So this is a universal or a general condition. This is a zonal, so it only occurs in certain planes. And these are axial conditions. And these are related to different kinds of symmetry elements. Some of these are, of course, related. So if you have a zonal that's due to a glide, you'll also have dependent axial systematic absences. And then you'd work your way through, well, I don't have any general conditions. Oh, I have zonals. And you'd find out, okay, that's my space group. So this is what we used to have to do before we had awesome programs that did this for us. Now that's what we do. But if you have ambiguity, there's only one way to sort that out, and that's unfortunately us. Okay, so now we've gotten to the part that everyone worries about. 1, 2, 3, 4, 5, 6, 7 steps later, we get to actually see if we can solve our structure and determine if we can get atomic positions from our data. So how does that all work out? Well, we're looking for electron density. So we have the Fourier summation here. I was told I didn't really need to tell you about this because you got that beat to death, so I won't. But up here, we're talking about the structure factor, which is the sum of the scattering factors for the atoms over different HKL. Those are the Miller indices of the reflections. And XYZ are the real space positions of atoms. So that's the ideal, beautiful thing, right? That's what we want, is the electron density. So rho XYZ. However, I won't get to that part yet first. So if we're looking at X-rays, our form factors for each atom, they drop off with angular resolution, which I think you should have already known that neutrons do not. You heard that already? Okay, good. All right, so we're back here. We want to go from our list of reflections. So we have H, K, L, intensity, and error. And we want to turn that into electron density. But the problem is this has a real component and an imaginary component. The real component is the amplitude. The imaginary component is the phase. And we don't have any phase information. None. Zero. Nada. Nope. So what do? Well, most structure solution programs use a combination of different methods. They use phase relationships. So we have things called negative quartets, where we have reflections that their phases are related because of their Miller indices. And we also use statistical methods. So in essence, as far as the time we've got in this talk, you're going to trust me, it's a black box, and we do statistical methods, and we get phase sets that produce realistic electron densities. So i.e., assuming that the electron density throughout space is positive. That's usually the base assumption that most of these programs make, that there is actually electron density, because the opposite of electron density is not physically reasonable. So that's the main assumption that a lot of these programs make. Here's a list of a couple of them that are really nice. It seems like someone comes out with a new one every year or so. Oh, yay, that's that part. Okay, and this is the idea of what we get. I don't know why that's shaking all of a sudden. Californian paranoia, earthquake, stop, drop, roll? No? Okay. All right, so this is the idea of what we get initially is we get a solution. So we get some electron density. And so you can see this is a map of, we have something very heavy here. So we have lots of our little gradient lines because there's something very large. And then we have 6, 7 rings. I believe I rendered these all at about 1 electron per cubic angstrom type area. So you can see, okay, we've got light atoms, something heavy, something possibly heavy but not quite in the plane, something weird over here. So we get a 3-dimensional map of where atoms could be. At this point, it's very could be, because we're dealing with statistical methods. We may not have actually gotten a solution that's a global solution. We may have kind of a local solution. So then we have to go through it with some chemical know-how or physical know-how of your system and decide if that makes sense. So in this case, this is a crazy finished version of a structure. So this had to go through a lot of iterations of, does that make chemical sense? If so, yes, great, we keep it. If not, then we have to throw it out and refine further. And we're going to talk more about refining after this. Because now we're into the death spiral of every new crystallographer's life. You've got data, congratulations, so happy for you. Come back to me when it doesn't work. Because unfortunately, this is where it all turns into a bit of a struggle sometimes. Because structure solution can be really exciting. I've got data, it looks great. And then you start to put your hopes and dreams on it. And then you have to do least squares refinement. You're like, oh, I saw this new molecule, it's beautiful. And I did least squares refinement, and it's gone. And, and I will give condolences, and I will tell you why it probably went away. But unfortunately, the proof is in the pudding. If you don't have a model that survives least squares, you don't have nothing. Sorry. Many a user's been very sad about that. But I got a solution. Lots of things solve. Not all things do least squares refinement. All right, so the cycle is, as I discussed earlier, we've determined some atom positions. Great, fabulous. Do least squares refinement. Oh, looked a little sketchy. You had some interesting correlations. You had some weird things pop up. So then you have to examine your atoms. Ooh, that carbon's 5-coordinate. Does that make sense? No. Why is it 5-coordinate? Oh, that other atom just kind of blew in here and landed. Well, you kill that other atom and see if everything can retain its chemical meaningfulness. Delete any other bad actors. If you find any other weird electron density that's not accounted for, well, I didn't think there was bromine in there, but maybe it's still in there. I thought it was a leaving group. It didn't leave. Okay, then you need to add that into your model. You've got your atom positions. You feed them back into another least squares refinement. They go through, and the scattering factors that we've got, our reflection list, is compared to a theoretical scattering factors list that your current atom positions make. Then they are compared. That's where you get the R values. So an R value is comparison between the observed and our calculated. So if this was our structure, we would calculate what the scattering factors would be for the structure, compare them, you get an R1. The weighted R2 throws in a weighting term that basically downweights the weaker reflections. So it's usually a bigger number, but it's actually a better indicator of quality. I don't care so much about a small R1 if your WR2 is ginormous. It's really, it says a lot there that you have a lot of weak data, that you're pushing the boat out and maybe refining on some noise. All right, so here is a list of some wonderful other places where you can get lots more information. This is, of course, not exhaustive. There's also an excellent book by Gio Cavazzo. It's huge. It has everything. I just don't use it as much as I use these two. I keep these two near my desk, especially Stout and Jensen. It's old, but it's still pretty valuable. Okay, so this is a good point where we can take a minute. If you have any questions, we're going to go a little bit high speed for a couple minutes. Any questions? No? I've been perfectly coherent? You know what time it is where I'm from? There's no way. No way. Come on. I could be making things up right now. No? Okay. So, at this point, I'm going to talk a little bit about what happens. Yes, okay.
I guess this is going like way back.
Okay.
But in this basic determination slide.
Yes.
Why are there like just all those extinctions kind of underneath what looks like the negative y of the origin? That was weird.
Okay, so you wanted to know why there were basically no spots under negative y. All right, let's take a little quick trip back there. That's a great question. So, in here, nothing there, right? So that has to do with actual diffraction real space geometry. We can't always access all the spots. So probably the most likely reason there are no spots here is because that's an area that was inaccessible with the diffractometer, with relationship to how the crystal was mounted and how we can move. So that's on a 3-circle diffractometer, and there is some definite dead space that you can't get the crystal swung around to. So that's probably what that is. In a perfect world, we would have a full sphere, complete sphere of data, but in this case, we do not. And that's probably behind the beam stop or very close to that area. And so it was masked off in the detector. But good question. Yeah, no, definitely you would think there would be all filled in, but those are really low angle reflections. So they're not always obtainable. You want to get as many of your low angle reflections as possible, but some you would actually have to do some gymnastics. Good question. Thanks for paying attention. I'm glad someone's awake. Okay. So this next part of my talk is dedicated to okay, you can do a crystal structure, that's great. Is there more you can learn than just a simple, low temperature routine data collection? So what can you do with more flux? Or just more time? Or more whatever? It doesn't have to be just synchrotrons. Synchrotrons help though, so this might be considered a slight plug for high flux sources. Okay, so why do crystals diffract poorly? This is true, right? I'm pretty sure that all of you who've done crystallography before have also been told, yeah, that didn't work. Grow it again. That's a constant refrain from the lab crystallographer. Nope, no good. Go grow it again. Well, why do they diffract poorly? But then there's also my business was, how can we make them diffract poorly? What can we do to them to extract more information while possibly killing them? And what can we learn from poorly diffracting crystals? And what do synchrotrons have to do with all this? Well, you might have already suspected the answer. So when we look at the spectrum of crystallinity, we have perfect diffractors. That is a perfect diffractor. So if we think of like silicon or diamond, where you have everything is very well aligned and you have diffracting beams that can be re-diffracted even, that's where you would have possibly extinction as a major factor. So this is a perfect crystal. They diffract dynamically with Bragg scattering. And we have good crystals. This is pretty much everything you've ever put on that got down to an R factor of like 2 or 3%. It looks really good. It's not perfect. It's got little regions that are perfect, though. So this is a mosaic region. This is a very fine, perfect little region, but it's slightly different oriented from all its neighbors. The long-range order is excellent, really, because each one of these little things is well ordered. But the mosaicity, i.e. the rotation between the different domains, it's a little higher than your perfect crystal. Poor crystals. So they still diffract, but they diffract kinematically. So Bragg scattering is still a thing, but the diffraction is limited because of poor long-range order. So something has happened that is the long-range order, because essentially diffraction is a measure of long-range order. So either there's positional disorder, where you have kind of a solid solution situation, where sometimes it's bromine, sometimes it's chlorine on your organic, or sometimes things are 3.5 angstroms apart, and sometimes things are 3.7 angstroms apart. You have libration, or you have not the most perfect orientation of crystals. So these can show powder Lowy rings due to mosaicity becoming microcrystallinity. So anytime you see those spots just kind of going on forever, yes. So that's where you're verging onto what I lovingly call a crowder, a crystalline powder. It's not quite a crystal, not quite a powder. Kind of wants to do both, but neither well. So that happens. And also you can see non-Bragg scatter sometimes due to thermal diffuse scatter. So this is usually the crystals we call the desperate. They're not always doing so well. We can look at scattering efficiency as being related to the wavelength of the X-rays coming in, but also inversely proportional to the volume of the unit cell. So a very large unit cell is going to hurt your diffraction intensity. Also, the structure factor, if you have all light atoms, it's going to hurt your intensity of diffraction. So we can also go back to the protein or the large. Yes?
The slide before this.
Yeah.
What does it mean by TDS?
That's thermal diffuse scattering. Yes. And I'm not going to talk more about that. That's a couple days worth. Okay. So we're talking about the structure factors here are, if you have all light atoms and you have a large unit cell, your intensity of diffraction is going to fall off. It's not going to be very good. Volume of the crystal. If you have a small crystal, you're also going to have a little bit of a problem, mostly because you don't have much of a volume for the beam to diffract off of. And this was all pretty closely looked to by Marjorie Harding way back in the day, beginning of synchrotrons. This was kind of the justification for, hey, we have crystals. They don't always work on lab sources. Can we use the synchrotron too, please? So this was the beginning. And I showed this earlier to you, but I'd like to take a little bit more time on it. So when we talk about B values, that's the old school version of U values, which we consider thermal parameters. So if your thermal parameter is perfect, then you will have this carbon atom will scatter out to really high resolution. The second you add on some thermal parameter wiggle, it drops off. And eventually it actually goes to 0. Once that goes to 0, it doesn't matter how hot your synchrotron source is. There's no there there. There's nothing left. It is waggling to the point that it can't be relied on for any kind of interference. So it is done. And this is something I try to remind people who said, well, I only got 1.2 angstrom data at home, and I collected it for 5 days, and I still only got 1.2 angstrom data at the synchrotron. I'm like, yeah, that's the point of limiting returns. You can't go and get more blood from that stone. It's done. You have a major disorder issue. And then you have to learn from that structure what you can. This was a calculation I did a couple years back looking at reflections from an ideal structure without involving U values. And then I added an increasing U parameter. So this would be an excellent structure. Excellent. If you're getting U parameters that are all less than 0.01, either it's amazing or you have a weird absorption correction issue, because that's almost to the point where it's too small. This is pretty normal. I would say getting a structure with U's of 0.02 to 0.03, okay, that's good. That's very typical for a good low temperature structure. This I would consider a little wobbly, but not bad. And this I would consider everything's doing this. It's never good when you see anything that has an average U value of 0.1. So we have a really strong reflection, some weak ones, and some decent reflections. And so I just took them and calculated how they would adjust with the various U values. The strong reflections stay strong. It's not surprising. But what you lose are the higher angle, higher resolution peaks. And those are the ones you want. Those are the ones that tell you in greatest detail the shape of electron density. So when you lose these guys, you're not getting a lot of information anymore. If we zoom in at U of 0.02, we can still get all these reflections, but adding in any more movement of your atoms is just washing away the higher angle reflections. So what does this mean to you? Well, if this is a real and valid problem for you, you need more intensity, or you need to fix this wobbling issue. Like if you have all your data sets collected at room temperature, you need to cool them down and see what happens, and see if you can drop your U values to get better diffraction. But definitely, if they still exist, if you can still get a tiny bit of diffraction from them, you pump in more photons. So that's the take-home message here. If disorder is an issue, then you need to have more intensity. Another thing that you need to think about when you're doing crystallography is the wavelength and the material need to be compatible. So we hear about protein crystallographers all the time because, everyone thinks that's the only kind of crystallography there is. And they do things the way they do because it's well matched to their systems. They collect data at 12 keV, or sometimes 8 keV, softer energies because they have soft materials, and they're trying to use that lambda to the third power relationship that we discussed earlier. They want to pump out the intensity of their diffraction spots. Now, if you're not working with soft, squishy proteins, you might need harder energies. If you're working with any kind of material, say a lead halide perovskite perhaps, you may not want to use 12 keV energies because they will get absorbed. You might want something more like 30. You're going to want something harder. You're going to want smaller crystals, but you're definitely going to want something more penetrating and less likely to have absorption effects. You also might want to think a little bit about absorption edges, because that's something you can run into that will really skew your absorption of your sample. If you're running into an absorption edge of a major element in your sample, you should think about that, because that could give you a lot of headache. This is where I'm going to tell you that your lab crystallographer is wrong. Don't hate me for this, Cora. Large crystals. When they tell you to go back and grow that new large crystal, there's no guarantee it's going to be any better. Because as you grow that larger crystal, it may accumulate more defects. So it may actually be worse behaved. It's very common, actually, for badly behaved crystal systems. I take a chunk, a smaller piece of that larger thing, because it's probably going to have fewer accrued defects, and it will actually match my beam size better. So bigger is not usually better, and regrowing it doesn't usually help. And rocking width is a factor because of the accrued defects. So you're going to have a worse mosaicity just because it's bigger in general. Okay, so that's my sermon on badly diffracting things. Now let's go on to, yes? Rocking width is your peak spread. So those spots that we saw in those images, how big they are is related to mosaicity of your crystal, and that's the rocking width. So basically the angular range that the crystal traveled to have that diffraction spot in diffraction conditions. So that width is broadened by the mosaicity of your crystal. And so the more defective and the worse your mosaicity is, the broader your peaks will get. Now, that can be a serious issue if you're working with a large unit cell and you need to determine your unit cell parameters. If your spots are overlapping, you get greater uncertainty. So the smallest rocking width is desirable. However, you can achieve that. Okay, so that's about how crystals can be bad sometimes. This is how we make them bad, or we at least abuse them. So my personal goal is to find as many ways to abuse crystals in life and get information from them while we're abusing them. So in-situ crystallography is kind of my personal niche. Application of a stimuli to produce structural change. I'm going to say that this one is the one I live with the most. It's high pressure. We're going to talk a little bit about that. Temperature is pretty obvious. We've already covered that. But you can also put crystals in an environmental gas cell. You can pump solvents out of them, flood them with a new gas. You can shoot them with a laser or LED diodes. And you can do electric or magnetic fields. These are all things that have been done. And if you think you have a material that needs this, you should definitely talk to me or someone else who works at a synchrotron who does such experiments, because it can be really exciting and interesting. A desolvation experiment, this is one we did a couple years ago actually now, where we had these crystals, dark red, and we pumped the solvent out of them. And then we took a new structure of them, and then we put a different solvent back in, and watched that solvent just go back into the same site. New solvent, same site, and then pulled it out again, and put back the original solvent. It was a completely reversible cycle. It was really interesting that the crystal could do all these transformations and not die, because it wasn't a very porous crystal either. So the mystery of how it could do that and survive and retain its crystallinity, that was pretty fun actually. This is our photocrystallography rig at the ALS. This is just a little ring of UV, actually these were blue/almost UV diodes that we have mounted around the crystal. This is our detector. It's not a welder's mask. It's a little hard to look at. But the idea is, here's our ring when it's not powered on. We have these LEDs. We have our crystal mounted basically in the center. We take a, we take a ground state structure. So we do X-ray diffraction on just the crystal before we've irradiated it. Then we irradiate it. And then we take another data set, see what's happened. And lather, rinse, repeat. Here's it lit up. And this is what we got on this very first occasion. We were able to watch the structure change. So this was a nitrosyl going from N-bound to O-bound. Not nitrosyl, nitroso. Nomenclature. It's been a while. So yeah, it was really exciting to watch this kind of transformation and watch the occupancies of the atoms switch over from completely N-bound to completely O-bound. This was a proof of concept experiment. We've done a lot of other systems since then. But it's pretty interesting to know that you can actually watch these metastable states grow in. This is our environmental gas cell. So if you look in here, this is a normal looking Huber head with a whole bunch of vacuum equipment slapped onto it. And right inside here is this. So normal mitogen loop with a crystal glued on the end. This is a glass capillary. We can pump it down. We can pull solvents off. We can heat it. And we can flow in a different gas mixture. And then we can watch the changes to the structure. So for example, I believe this is cobalt CPO26. It comes hydrated. So these are the water molecules right here. And we can pull them off. And not with Photoshop either. Just pull them off with heat and some vacuum. And then we backfilled with NO. So we could watch the nitrogen position fill in, and then we have some disorder in the oxygens, but definitely fully occupied by the end of this experiment. We also did the same thing with SO2. So these are options that you have. If you have a MOF, if you have something you think would react with the gas, you don't have to guess about what it's doing. If you can get a single crystal, you can actually try and watch it, which I think is pretty powerful. There's a lot to be said for gas sorption measurements ex situ. But to actually observe the atom positions crystallographically is pretty solid proof. My personal love. It's kind of a love-hate relationship. I call it the original first world experiment. We put a crystal in between two diamonds. Then we put a ruby crystal next to it. And then we put it inside a hole of rhenium. And anyone who's ever bought rhenium, it's expensive. So this is not a completely accessible experiment. It's definitely first world. But it does produce a lot of really interesting transformations structurally and chemically. These are two of our diamond Anvil cells here. So if you look in this center here, we have a diamond. And you can see kind of one of the diamonds shining right over there. Here's a blown up picture of it. So here's the diamond in what we call backing seat, usually made of tungsten carbide. This is it says here tungsten gasket, but people are kind of split between whether they like tungsten or rhenium or stainless steel, depending on how high the pressures you want or what your other needs are. And then this one is a Merrill-Bassett design, so you tighten the screws and you apply pressure. We actually throw in some Belleville washers to give it a little bit smoother application of pressure and take some of the mechanical advantage away. And this is what it looks like when it all goes pretty well, although you can see this sample chamber hole isn't perfectly centered on the diamond culet. That happens sometimes, mea culpa. But here's our crystal, and here's our two little ruby spheres. And so this, we're looking through the diamonds. And so we'd be shooting straight through the diamonds, so we're also going to see diamond diffraction. So this was a family of compounds that I first got involved with the high pressure thing seriously. It's with a collaborator. They're the Zinc-Alkyl gate family. And so right here, these green atoms are zincs, and they are coordinated to a alkyl phosphonate. So initially we thought that the zinc would be the rigid linker, and the alkyl groups would be the flexible, compressible moieties. That's how we thought this through. We're like, oh, let's put it under pressure, and we'll watch those squishy alkyl chains flex and bend, and probably the zinc would do nothing. Seems reasonable, right? Well, that's all well and good until you realize actually what happened is we put the pressure on, so this is the ambient pressure, and this is at 9 GPa. And if you look at the torsion angles, those alkyl groups didn't change at all. They were rigid. They didn't do a thing. They laid down, but they didn't change. What changed was the coordination around the zinc. So that was kind of surprising. We kind of thought in that whole metal organic framework mindset that our metals are the anchors and the linkers are soft and squishy, but actually our alkyl groups were rigid. And it was very reversible. We took this compound through a couple of different pressure cycles. Crystal didn't care. We took it out of the DAC, put it back on the diffractometer, still looked great. So it was a very robust compound for this kind of work. It definitely surprised us with how it adapted to the high pressure. Okay, so I think I am about to wrap it up, so I'm going to give a couple of closing thoughts. I hope that you all think crystallography is awesome and you all want to do single crystal experiments now. That's a given. I didn't need that on the slide. But I do think that in situ experiments, if you have an interesting system, you should definitely try and push to learn as much as you can from your system. Produces degradation of the crystal, but you learn so much. And of course, poorly diffracting crystals, you need to go to a synchrotron or a high flux source, definitely. Don't waste your time on your lab source for 4 or 5 days when you can do, 3 or 4 hours at a synchrotron. And that's, of course, my endless commercial for synchrotron radiation. And the advanced light source is supported by the Director, Office of Sciences. Yes, that is our view from our user support building. Yes, I eat there every day and have lunch. And I'm also supported by COMPRESS, the Consortium for Materials Properties Research in Earth Sciences. No, I'm not a geologist. Thank you very much for your time. Yes, back row. So in diffraction experiments, we are generally not worried about beam spill-off. We have designed the geometry such that we have beam stops to keep the beam from impacting the detector or any sensitive materials. because we're not usually doing a photons in, photons out type of analysis, spill-off is not detrimental to the diffraction experiment usually. Yeah, if you were doing spectroscopy, where you actually need to know input flux versus output flux, I can see that being an issue because you don't have them all going into your sample, but we don't actually do that measurement. So, good question though. Yes?
So, how do you define
So twinning of the crystals. I didn't even really get a chance. I didn't want to go down that rabbit hole, but definitely that is a commonly encountered problem. So twinning is usually defined as crystals with domains of similar unit cells, but different orientations. So you have the same unit cell, and sometimes they're intergrowth, where you have a unit cell pointing this way, and propagating at different directions. Usually you will see two independent lattices in your diffraction images. It's gotten to the point where most crystallographers I know, myself included, we can look at about 10 images and go, that's a twin. So actually, if you want to see twinning, this is where I may have fibbed slightly to you, way back in the talk. This picture, this is actually a twin. So right there, you see those two spots next to each other? They're next to each other because they're two different domains. So ideally, in a crystalline lattice, you see spot, 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 regular intervals, never too close to each other unless you have a really long repeat in one axis direction. And then, if you do have a long repeat in one axis direction, you will see the spots proceed in a line. But the fact that this guy looks a little bit off from the general line of spots progressing there, immediately, twin. And it was a twin.
So
yeah.
You're saying it's from a different domain.
Yes.
How about the chiral nonsense?
So if you're looking at chiral twins, that's usually you're looking at the FLAC parameter. And so if you have chirality present in your system, then you know that you cannot have space groups that have mirrors if you're enantiopure. So if you have an enantiopure compound, then your space group should not have any mirrors or inversion centers. And so if you are seeing your refinement not progress well with a chiral compound, you should be checking your FLAC parameter. FLAC parameter is a measure of the bivote difference, and this is getting to the edge of what I usually explain. But if your FLAC parameter is non-zero, that usually indicates that you have chiral twinning. And so that can also indicate that you're not as enantiopure as you thought. So, or if there are a lot of space groups that are, oh God, the word escapes me. Well, yeah, no, I'm not thinking enantiomorphous. There's also the like P61 and P65. So those are actual chiral enantiomorphic space groups. They are twins, usually. So if you have a twinned P65, it's usually P61 is the other component. So.
Another question would be, at what point point defects and dislocation, changes the symmetry of a crystal, and it cannot be found in unit domain? Or does it happen at point defects and edge dislocations, or any type of types of dislocations?
So the question is, if you have edge dislocations or defects in the crystal, does it limit your unit cell determination? So it can. So usually what I see primarily that interferes with unit cell determination is when you have the word just so you have stacking faults. So your crystals are plate-like and you have imperfections in a platey direction. And what you usually see are spots that progress forever. And so where other spots cleanly appear and disappear off the images, you have some that are strongly affected by the stacking faults, and they're very ill-determined. So in that case, if the stacking faults were so great, then you're not really dealing with three-dimensional order. You're only dealing with two-dimensional order. And so then you are left with usually one poorly determined direction. And so in that case, it's how useful is that? You know, if if you have a reason to believe that that ill-determined direction you can determine with some other technique, then at least you've gotten 2 out of 3. I wouldn't trust any structure from that data usually, because you've got that issue with one whole direction of reciprocal space. But as far as unit cell parameters for the other 2 directions are, they can be hugely helpful, especially when you're looking at thin film growth. You know, having 2 out of 3 is sometimes all you need for thin films and systems that are not going to be looked at as a single crystal usually. So it's still information, but
Can you do tomography to actually see that or determine the structure? Because, like we said, it becomes 2-dimensional.
so once you have more of a continuum effect, you're going to have to be looking at spectroscopies or other techniques that deal in non-Bragg scattering techniques. So maybe SAX, wax, PDF. Those are what you'd have to use if you were getting into a point where it's non-Bragg, it's non-periodic, but you want to know at least nearest neighbor distances or something, then you have to look at the other non-Bragg type techniques. So, yeah. Yes?
I was just curious, looking at your pressure cells.
Mm-hmm.
Obviously, we talked about rotating the crystal.
Mm-hmm.
It doesn't seem like you have a lot of play to do that at a particular pressure with that window setup.
Yep.
So you pretty much have to collect what you can through those windows and disassemble it and try and get it to the right pressure again?
No, so yeah, that is a major issue. So what he's asking is, with the diamond Anvil cells, how much does it limit your accessibility to reciprocal space? And this is a huge issue. So you'll notice that the DACs that I showed are Merrill Bassett, and we've actually gone through a lot of trouble to try and optimize the opening area of the diamond to the greatest extent possible. So if we're looking, this cone right here is an 80-degree opening cone. So we can rotate the DAC 80 degrees across the face and collect data, and then we can rotate and scan across the other side as well. Usually, for a single crystal experiment in a DAC, you want to have the greatest opening angle possible, and you also want to have about the hardest X-ray energies as possible to compress reciprocal space down small enough that you get as much data past that, that issue. So you definitely won't get all the data. This is why high pressure people love high symmetry systems, because then it's a smaller chunk of reciprocal space they need to access. But with the opening angle and harder energies, you can get very good reciprocal space coverage. I figure if you can get 75% of reciprocal space, then you're ecstatic, generally. Right. I'm seeing hands going up and down over here. Yes?
What do you backfill the diamond Anvil cell with to get a hydrostatic pressure?
So it depends on the pressure range we want to go to. So there are different pressure transmitting medias you want to fill the sample chamber with. For super low pressures, I don't want to go over 2 GPa, I've used Krytox, which is polyperfluorinated oil, but that becomes non-hydrostatic at about 2.5 GPa. Above that, there's a 4-to-1 methanol-ethanol mixture that retains its hydrostatic characteristics to about 10 to 13 GPa, depending on who you ask. And after that, we try to do gas loading. So we have a gas loader at the ALS that we can load with neon or helium. And both of those are excellent pressure mediums pretty much all the way up. Once you get past a certain point, you're not going to find anything that's perfectly hydrostatic. So you're just going to have to kind of cope with some of the strains that are on the crystals and do the best you can. So, yeah, good question. Yes?
This is a high-frequency experiments I did before. I witnessed a permanent change of the material properties
Mm-hmm.
of the decompression. I'm just wondering, can that be possible due to materials being compressed to metastable states or there is structural?
Yeah. Yeah, so the question is, sometimes in high pressure experiments, he's seen crystals that undergo irreversible changes. And that can be a metastable pressure-induced form. You could have actually undergone a reaction of some sort where you've produced something that's a different energy type situation. That's definitely not unheard of. So, yeah. Yes?
What's the lowest temperature
So the lowest temperature that we can achieve on 1131, which is the small molecule crystallography station, we have a open flow helium cryostat, so we can go to about 20 K reliably. People who have closed cycle cryostats can go much, much, much lower, usually down to the millikelvin is where it has been done. The problem with any kind of closed cycle cryostat, though, is you have the same kind of angular restriction that you would run into with a diamond Anvil cell. So it would have to be an instrument that's designed for use with that and is robust enough to move a heavy cryostat. Got a couple more minutes? Any more questions? Oh, yeah. Mm-hmm. Yes, so if you guys have any questions about doing experiments at the Advanced Light Source, I can definitely give you information on that. The Advanced Light Source website, which is www-als.lbl.gov, has some resources on how to become a user, and you can always email me, cmbeavers@lbl.gov. I will answer any questions about anything you want to do crystallographically. So.